Hi there, my name is Redone and I'll be discussing the design and manufacturing automation of a propeller. When designing in CAD, not everyone has equal level of skill when starting off. People learn at different paces and can grow at different rates. With the level of practice given to students within the curriculum, it may not be enough to just familiarize themselves, but also fully understand all the tools they are working with. So creating complex geometry like that of a propeller and its blades, it may be completely out of the question even if the person follows a guide. At King's College London, one of the engineering group projects the students complete within the first academic year is the creation of a small RC boat. The goal of this project is to be able to navigate the boat into the ping pong balls and be able to collect them with a collection system they create. The project itself gives the students free rein to test a lot of different layouts and setups to get the correct design boat with the correct aerodynamics and systems before the demonstration day. However, they have no control over the propellers and are given a standard free-blade one by default. The use of automation on the design would allow the students to be able to come up with their own custom propeller designs and test how they could impact performance of their boats. This gives them a hands-on experience with using the utility tools within Fusion 360 and could potentially allow them to use other machinery not normally used, such as the CNC machine, during the manufacturing of their propellers. The first stage to automate the design process was by making use of an open source tool known as OpenProp that ran within MATLAB. When running the tool for the first time, the students can feel overwhelmed with the amount of values, however the tool is very intuitive after overcoming that hurdle. The list of values under R/R determines the current position along the overall length of the propeller. The list of values under C/D determines the diameter of the propeller blade with respect to the values under R/R. The list of values under CD represent the drag felt by the propeller blade with respect to the R/R values. The list of values under TO/D represent the thickness of the propeller blade with respect to the R/R values. When running the tool after putting in the desired values, it is important to focus on KQ, KT, and efficiency values. The KT and KQ determine the maximum thrust and torque the propellers can produce. Both go in tandem with a high torque value determines a higher rotational speed, and thus a higher thrust is produced. The higher the propeller efficiency, the better the propellers. This section also provides a useful graphical representation of the thickness and diameter of the propellers with respect to the distance against the blade. These prove useful when trying to modify a propeller's shape to try to increase the efficiency of the propeller. When finished with OpenProp, a folder will be generated. This folder will hold multiple text documents, each containing coordinate values which when combined create a single slice for propeller known as an airfoil. To import these files into Fusion 360, they must be converted into an Excel spreadsheet format. To bulk convert all the files, command prompt is used, and by utilizing the when function, it creates a copy of each text document in the folder and converts those copies into Excel files. From here, the files can be imported utilizing an updated version of the import spline CSV script. This script essentially imports all the Excel files within a single directory. Finally, the layers can be manually lofted together. The reason the stage cannot be automated is because of the edge of the propeller through lofting doesn't match the edge of the propeller blade itself. For the subtractive manufacturing side, the CNC machine was used. As the title suggests, layers of material are removed from the stock material to produce a product. The block material could range from a piece of metal to a piece of wood. The method behind producing propeller through the CNC machine was first within Fusion 360's dedicated manufacturing space. Tool paths are generated. What this consisted of was first taking the measurements of the end mill bits and the CNC machine within the makespace to simulate them within Fusion 360. The end mill bits, which are essentially act like small blades to cut the materials chosen, was a 2mm flat end mill and a 2mm ball end mill. From here, 2D face was done with the flat end mill. The purpose of this tool is to provide a smooth, quality surface to the stock. This ensures the surface being worked on is also fine and clean and easy to work with. From here, the ball end mill was used to do a 3D adaptive clear. The ball end mill is utilized to cut into the material to produce the object itself, and thus the 3D adaptive clear is essentially what produces the product. From here, the toolpaths generated need to be converted into a form the CNC machine would understand, and thus the files are exported and converted to G-code. When using the CNC machine, multiple issues were ran into. The first major issue was due to the clamping of the stock down onto the CNC machine bed. The first approach was to simply make use of double-sided tape. This method proved effective at first, but it was then dependent on the size of the stock being used and the material type. For example, when jello tongue was used, using double-sided tape worked perfectly fine as the wood chips made less refined and thus couldn't get underneath the double-sided tape layer. However, when using plywood, as the chips produced were more refined, it was easy to intercept the double-sided tape layer and declamp the stock from the CNC bed. Another issue faced was the surface area of the stock used. When setting up the stock within Fusion 360, a relative size stock was chosen to produce the propeller. When using the exact size due to the stock being clamped down using double-sided tape, the feed rate and the cut rates chosen were too high and the forces felt on the stock due to the bits were too high, and thus the stock very easily became misaligned. The only solution would be to produce a propeller with a much larger stock size, but in doing so, the time taken to machine the propeller would have taken too long, making it unreasonable for the students to use. The machine itself is 3 axes, and thus only half of the propeller can be produced within one go, as the 4th axis isn't available. If it was, it would be able to rotate the entire stock, simplifying the process a lot. However, by creating a negative inverse of the propeller through the use of support lobes, it would have been possible to create the other half of the propeller. However, more issues were faced when doing this section as well. The first issue was method of attaching the negative inverse to the stock material. Using double-sided tape had no effect. Using a screw within the hub didn't provide enough of a strong connection. Ideally, more screws would have had to have been used, but it would require the toolpaths within Fusion 360 to recognize and ignore the screws themselves. Another issue was the fact that the datum point of the negative inverse didn't match the mirror of the original datum point. The datum point is the reference point the machine uses when it makes any form of cut, and is done with respect to how far it is from the datum point. This caused propellers with misaligned faces to occur. When producing the propellers via the 3D print, 3 different materials were used. In this case, resin, PLA, and ABS carbon fiber were chosen. The original smaller sets of propellers all contained issues, excluding resin. This is because the minimum thickness the 3D printer could detect wasn't small enough to register the minimum thickness open prop utilized to create propellers. Once the thickness value was upscaled, the 3D printed PLA and ABS propellers came out with a good finish, smooth surfaces, and had no form of brittleness around the propeller edges. Overall, the CAD design of the propeller has significantly been streamlined and is now much quicker to do. Students would be able to produce propellers very quickly with little time spent. This would allow them to learn the mathematics behind the functionality of the propeller to implement them into their design without spending ample time on trying to make a propeller by following a YouTube guide. Producing a propeller via a 3-axis CNC machine may be undesired. This is due to too many unknown factors having to be dealt with to reduce the probability of failure, and the fact the timing required to produce one propeller could take upwards of 6 to 8 hours. This on its own demonstrates the superiority of utilizing 3D printed propellers, as multiple propellers can be 3D printed within one and make it much more viable.